Good morning. The International Magnesium Association is welcoming you for another event of its series of related to sustainability, with the main focus today on recycling. In the name of our President, Hartmut Fischer, and our European Chairman, Ken White, a good morning, a good day, a good afternoon, wherever you are listening today. My name is Martin Tauber, and I'm the representative of the IMA in Europe. Before we start, a few practicalities for this webinar. You as a participant, you are muted, but you can ask questions in the chat functions. You can use the chat functions anytime. The presenters see that as well, so they can tackle the question during the session. If we have time, we take the questions after the session or as a wrap-up of the whole webinar today. We will make the presentation available for everybody, and we'll also record the whole session and put it on our IMA YouTube channel. Today's topic, recycling, is a very important topic in terms of resource efficiency and also for less energy consumption compared to the primary process, the primary production. Global policy making places recycling more and more in the forefront. For instance, in Europe, just recently, a next decision in the Critical Raw Material Act was taken for a benchmark for critical and strategic raw materials to have a recycling benchmark by 2030 of 25%. And of course, that includes magnesium as well. So magnesium is a very important topic for our industry. And today we hear about this from European, from North America's perspective, from international speakers, from their companies, their contribution for more efficiency, innovation in that field, and of course for reducing CO2. So with this, I open the webinar with our first speaker out of 5 speakers today. And it's a pleasure for me to introduce Elmar Bey to you. Elmar Bey heads the Material and Process Application Complete Vehicle Department at DLR in Germany. He has a degree in mechanical engineering and a PhD, and he has a board of directors position in the IMA as well. And since 2001, he is also heading our committee as a chairman of the Sustainability Committee. So with that, please, Elmar, and you will give us an overview and introduction to IMA sustainability work with a focus, of course, of recycling.
Thank you, Martin. So if you stop sharing your screen, I switch to mine. Thank you, and hope that it's working now. Everybody can see my screen. So thank you, Martin, for the introduction this morning. Good morning, everybody, or good day, wherever you are in the world. I want to give you a short overview about our view about recycling related to the Sustainability Committee of the IMA. And as Martin mentioned, I'm leading the Sustainability Committee since the establishment of this committee in 2021, since 2 years now. I'd like to give you a short overview. The history of the Sustainability Committee was that we established it in 2021, recognizing the relevance of the sustainability topic. Since that time, the member count has doubled, and we have a contribution of the entire magnesium value chain and also with a global presence in our committee. So that's very good that we have here a large support from many members of the IMA. Since 2021, we have established 2 working groups. The first working group is about green labeling with the global metric system. You all know that labeling the sustainability factors is not that easy, and we need to have an agreement about a standard, what we will use, how we will do an LCA, for example, and how we communicate this to our customers worldwide. So that's the topic for the first working group. And then we have another one, which is looking into alternative production methods and energy saving technologies. So to share information about opportunities to improve processes. And the third working group on recycling, which is the topic of today, is planned to be established in 2024. So if people here in this audience are interested and competent to support these activities, they are warmly invited to join our sustainability committee and support these activities. One activity what we have done about 2 years ago is that we discussed sustainability statement with the members of the IMA and the committee members to really highlight the next steps what the International Magnesium community is working on. So sustainability will be a guiding principle at all levels of operation. And the mission, what we have here, is to strive to reduce the impacts of greenhouse gases and natural resources by applying more sustainable technologies, using more renewable energy in our production processes. Then we want to continuously reduce the negative environmental and social impacts within the whole value chain. And what is important for today, we strive to improve circular economy approaches for magnesium to make end-of-life secondary magnesium a useful source of greener material. That's the overall concept, what we are working on in several activities. And hopefully you will learn today what single IMA members are contributing to these objectives. When it comes to magnesium, many people think, oh, can we substitute it? Is there an alternative? Why is magnesium so attractive? So why is it worth fighting for magnesium? So the one topic is lightweighting, but not only in its pure application. We all need to know that magnesium is one of the most relevant alloying elements for high-strength aluminum. So the topic when it comes to sustainability of magnesium is not only related to the magnesium itself, it's also related to other industries, which are, for example, very relevant for the transition into electromobility, where high-strength aluminum is largely applied. Then when it comes to the highest lightweight potential, then magnesium is the top choice of material because combined with the lightweighting and with other relevant factors like recyclability, costs, and available manufacturing processes, it's really a very good choice of material. So we shouldn't get rid of that opportunity regarding making vehicles more efficient regarding their energy consumption. And what many people also are not really recognizing is that in automotive industry, the lightweighting effects, when a car is produced, they extend to the second and third lifetime of a vehicle. The car makers typically calculating the first use phase, which is about 150 to 200,000 kilometers, maybe in the premium sector a little bit more. But then the car have a second and a third life in some other markets, and the lightweight effects, what I bring in the first in the production, then they will extend and will be valuable also much longer than typically calculated. The current situation regarding recycling, we will learn a little bit more today, but as a short overview, Magnesium recycling is well established for the pre-consumer scrap categories, for example, from casting processes, like you see it here on the top right in this picture. So that's state of the art. And the ISO standards, they allow for considering this kind of material as recycled material, even if we all could also consider this material as processed primary, because it hasn't seen a use phase at that state. But that's accepted and is also accepted for steel and also for aluminum. So there we follow the same standards. Maybe there will be a change in the future that activities, initiatives like the Science-Based Target Initiative will discuss this and will change this in their own metric so that the categorizing of those material streams might be changed in any way. We don't know that. But today the situation is, if we think about magnesium scrap, which is going into the aluminum industry, which is also quite common, the aluminum industry, they have established the ASI, Aluminum Stewardship Initiative metric, which is widely used in the industry, but this is not counting the magnesium content. Alloys with less than 10% of the alloying elements are counted as 100% aluminum in their metric. And that's a critical point, because therefore the magnesium, which is implemented into the alloys, disappears from the market without generating a recycling credit. So magnesium is used beneficially, but it doesn't get a benefit for itself and for the magnesium industry at the moment. And so at the end, it's a strong need to find better ways to utilize the end-of-life scrap from magnesium directly within the magnesium industry, where it is counted as a credit, and to effectively substitute primary material there. So that is to be discussed, and that's also something what we will discuss in our new working group. We have also discussed in our sustainability committee general pathways to make magnesium a greener material for the future. So lowering emissions in the primary production is one of the top priorities what we have. And so the primary producers, they know that they urgently need to develop a decarbonization roadmap and invest into greener processes. That's ongoing yet, this discussion. Then there is a need to regionally diversify the supply chain. At the moment, you all know that in the European Union, most material comes from Asia, but there are projects now on the way that we also have a primary material supply from here, from the region. So speaking for the European side. So, and then at the end, the whole process will be most successful if the customers are not going away from magnesium usage, but they continue use it, but they look into the supply chain and request those points from their supplier. So that will be the most efficient way to change something in the supply chain, if we use the market power what the customer side have to influence something. Coming to an end, so we all need to look into our scope 1 and 2 emissions in our specific processes, and that what I said before, utilizing recycled material more efficiently, that's very important. And you see here in this table what you can reach. Even if you start with not the greenest primary magnesium, you can change it into a greener material streams if you use a higher recycling content. So that was a short introduction into what we are doing in the sustainability committee. And if you are interested in supporting this activity, we are quite happy about that. So then with this, I would give back to Martin and for the other presenters today. Martin, you are muted.
Thank you, Elmar. we have one questions which I can answer quickly because it was only an introduction. You said that the ASI Aluminium Stewardship Initiative counts 90% and 10%, let's say, but the definition is from ISA, so as far as we are knowing, that there is 90% is 100%. So if there is 90% aluminium, it counts for the LCA calculation for ASI for 100%. Okay, thank you, Elmar. I give the floor to the next speaker. It's welcome Frank van de Winkel from TOMRA. Very happy that he is here today. Frank studied waste management. How can it be something else?
Of course.
And he started his career in a company called Como-Das GmbH in Germany, a specialist for sensor-based and sorting equipment for the metal and mining industry. This company was then acquired by TOMRA, and so he joined TOMRA and also went to North America and was responsible for the North American and Australian markets. And today he is the market strategy segment manager for the metal sorting business with TOMRA. And his presentation will be about sorting scrap metal by alloy composition and looking closer into the LIBS sorting technology. Thank you very much.
Very good. Thank you, Martin. What an introduction. It feels like I need to shorten that one. So thank you very much. Good. I'm flattered to be here. Thank you, Martin, for the invitation. When Martin and I first talked about this, I was actually saying, you know, TOMRA, we have sorting technology for the aluminum industry, and I was a little unsure if this sorting technology actually would make it interesting for you. But he convinced me that, yes, this actually could be a nice fit. So I said, yes, of course, I'm happy to present and also to learn from you on the magnesium industry. So with that, having said that, I will start my presentation on scrap sorting, metal scrap sorting by alloy composition, LIBS sorting technology for the recycling sector. And I have, and I hope you can see my screen. Martin, can you not? Good, super. Then I will use the next slide. I have a quick agenda. We will talk as it is, and only with one slide, about TOMRA and TOMRA recycling. Then I would like to talk about megatrends leading to certain activities in the recycling industry on the example of aluminum recycling. And then the main point, and that's why Martin invited me, I would like to introduce aluminum scrap sorting by alloy composition. There we have a new technology, which is called our TOMRA AUTOSORT Pulse, which is LIBS sorting technology. And I will give you two examples from the industry, one on post-consumer scrap and the second one on post-production scrap. And then a quick excursion on a research and technology transfer project that is funded by the German Ministry of Economics. That's the agenda. And as I said earlier, Martin, in our pre-discussion, I probably will run out of time. So I will try to speed up. Good. Next slide. Let's talk about TOMRA. Who's TOMRA? We are a publicly listed company listed on Oslo Stock Exchange. So TOMRA actually is of Norwegian origin. TOMRA, as the public listed company, we have about 5,000 employees globally. And we had in 2022 a revenue of about 12.2 billion Norwegian crowns. The Norwegian crowns, because we're listed in Oslo, that equates to roughly a little bit over 1 billion euro revenue in 2022. And how does TOMRA achieve this revenue? TOMRA actually wants to lead the resource revolution, and we do this by working on three business streams. One is the business stream of TOMRA Collection, and for all of you who have a deposit system on their drinking bottles, on their beverage containers, you might know then reverse vending machines, deposit machines, and that is actually what TOMRA Collection does mostly. So they provide deposit return schemes, systems, sorry, not schemes, systems, so the machines for this into many countries. And TOMRA collection thereby makes about 50% of TOMRA's revenue. So that's the collection side. The other side is the sensor-based sorting side. And there we have two business streams that both exclusively work on sensor-based sorting. One is the food business stream, and there we do everything from, for example, potato sorting on the harvester to fruits, fresh fruits, but also meat and fish sorting and measuring to increase resource efficiency. So that's TOMRA sorting food. And then we have TOMRA sorting recycling. And in recycling, we do sensor-based sorting for the waste industry. Waste meaning plastic, packaging, wood, and of course metals. And just to give you the splits, in the recycling industry, we probably make about 20% of TOMRA's revenue, and the food industry does 30%. In the recycling industry, we have about 9,000 units globally installed with a continuously growing network of customers. So that's enough on TOMRA, and I spent some time on it. Let's talk about then the metals industry and the global trend that I'm currently seeing, and probably you see this as well. I mean, we have the mega trend of climate change currently ongoing, which leads to a race to carbon neutrality, which is important for us to get there very quickly. And we have several states and countries and regions have pledged carbon neutrality by the year of 2050 or 60. With goals. And on the top of that, we have, for example, local initiatives like the European Green Deal and the Fit for 55 initiative, where we have legally binding committed to reduce climate gas emissions by 55% by the year of 2030. So those global trend, carbon neutrality, actually has impacts, as Elmar already said, has impacts on producing industries and the metal industry. And of course, it has an impact on the aluminum industry. And there, I think those facts and figures probably are known. Aluminum is very carbon intensive to make, so the problem is very big. And when you make aluminum out of the primary raw materials and you use energy from fossil fuels, coal or natural gas, on a global average, you are somewhere at 13.8 tons of metric tons of CO2 equivalent per metric ton of aluminum produced. Those are numbers that I learned 2022 in Chicago on the Harbor Aluminum Summit, and I guess they are somewhat still relevant. Now, that's carbon intensive aluminum. If you want to decarbonize this production process, you can first of all change your power source. Going to renewable energies, hydropower or solar power still doesn't bring you down to the zero target. It brings you down to an average of 2.2 metric tons of CO2 equivalent per metric ton of aluminum. So we're still not there. We need to reach this zero. And it is true for the aluminum industry, and to what extent it is true for the magnesium industry, I don't know. The aluminum industry only can reach those goals if they try to substitute as much of the primary metal production or primary raw materials by scrap metals. Then they get to what Harbor called super green aluminum alloys, and what I've seen also to be named as close to zero aluminum alloys or near zero aluminum alloys, which is then at 0.2 metric tons of CO2 equivalent per metric ton aluminum produced. So that's kind of the pathway the aluminum industry needs to take. So they have a lot of decarbonization efforts, amongst which one is utilizing more scrap. Problem is, if you want to use more scrap, especially on aluminum, then you need to counter the problem of having many different alloys. And aluminum, as you know, bonds with any, because it's very active. Once it bonds with an alloying element, it actually will not want to give up of that alloying element. So we need a technology to turn mixed scrap into something that can be utilized in the production of certain metal products. In our case here, for aluminum sheet materials. And the product that we introduced to the market is based on laser-induced breakdown spectroscopy. So it's called our AUTOSORB Pulse. And actually what you need and what is the core principle of this is an elemental detection of the material that you want to sort. So the principle itself works with a high power pulse laser, which emits laser energy onto a target material. And this target material, in our cases in the scrap industry, will be a piece of scrap. The laser hits and is focused on this target material. It will ablate a certain amount of this material, tiny little bit of matter. It will add additional energy and thereby ignite a plasma in which you will have free electrons. The moment that you actually switch off the additional energy, those free electrons will try to recombine into their original state. So they want to get stable again, and thereby they emit specific light, and this specific light is actually specific to the elements that were present in this target material. So actually I can collect this light emitted by a spectrometer or by optics, and then by a spectrometer I can analyze this, and I can say two things. I can say on a qualitative base that this material was aluminum and had certain alloying elements in it, magnesium, silicon, or whatsoever. And like you can see on the right side, I actually can also analyze on a quantitative level how much of those elements were present in the target material. And thereby I can actually tell one alloy from the other, and thereby I can analyze and then hopefully use this information to sort certain scrap materials. And that's the principle that has been implemented into sorting technology. And we actually do it, have this implementation, or we're working on this since 2003 and earlier already. So it takes a long time to develop a good and working technology, especially when it is so complex like LIBS. And we actually have a patent. To be honest, the patent has expired, but we originally started with Fraunhofer ILT in Germany to develop this. And the patent is, it is comprised of laser, then a focus unit, a scanner, an XYZ scanner, so that the material on the conveyor belt can actually be reached by this scanner. And then the plasma gets ignited, and we collect the material via a beam splitter into a spectrometer. And before that, we actually need to analyze where is the particle on the conveyor belt, and we do this by means of a 3D laser line. And I have a quick video so that you actually can see what is going to happen. You see here, I will talk you through this before we start the video. You see here the red line, which is a line laser. It has nothing to do with the LIBS laser. The red line actually will identify that on this machine, there's a particle on the conveyor belt. So we will collect geometry of the particle, position of the particle, so that the LIBS laser, and you already see here this white flashing light, actually can find the particle, can focus the LIBS beam on the particle, and actually analyze what's in the particle. And that's what we do in a relatively high speed. The conveyor belt is running at 3 meters per second, 590 feet per minute. And the material in the video, it will come in from the left, and it will be transported to the right, and that's what you're going to see. And it actually plays rather quick. And you see that we find with the LIBS lasers, plural, we actually find each and every particle on the conveyor belt, and so can detect the composition. And that is then how our AUTOSORB Pulse technology is sorting the scrap, analyzing the scrap, and then we sorted the scrap actually with this machine, which is currently available in our test center in Germany. We are based near Koblenz, And there we have this machine implemented. It's a big block of sorting machine. On this picture, actually, the material comes in from the right. You have a conveyor belt length of about 5.5 meters. You have a sorting width of 1200 millimeters, which is 48 inches. The conveyor belt runs with 2.5 to 3 meters per second, up to 590 feet per minute. And actually, this machine then is built in a way that it fits into an oversea container. And it's also built very safe because we have actually LIBS lasers in there that have laser class 4. And we actually protect each and every axis so that nobody can get hurt. So the machine itself will be or is rated as a laser class 1 device, like your Blu-ray player at home, if you still have one. The ejection of the material actually happens pneumatically into a drop fraction and into an ejected fraction. So we have valves across the conveyor belt section at the end. Every 6.25 millimeters, we have a valve and a nozzle that then can eject the particles into an ejected fraction. And this machine is now used for, in our case, in our example, for alloy sorting, aluminum alloy sorting, but you can transfer this aluminum alloy sorting into many other metals potentially. And we are focusing currently on the aluminum rod alloys. So everything that can make a sheet or an extrusion profile and the scrap. And the aluminum alloys are structured by groups 1 through 8,000 with main alloying elements. But as Elmar already said beforehand, the main alloying element doesn't mean that there are not any other elements in there. The 7,000, for example, already has also a high magnesium content. You see here that 2 and 7,000 for us, at least in the point of scrap sorting, are already clarified and solved by X-tract sorting. So when it comes, or X-ray transmission sorting, when it comes to LIBS sorting, we are currently very much focusing on 5 and 6,000 alloys, but also on the 3,000 alloys that are part of this. And we hit a certain other problem. We hit the problem that within the 5,000 groups, we have actually increasing magnesium content. So from 2%, 2.5% to 4%, 5% magnesium content, everything is possible. And the 6,000, you see, you also see some differences in alloy compositions on magnesium, silicon, but also on copper. So those are our challenges. And I would love to give you a quick example on post-consumer scrap applications and how this is sorted with LIBS technology. I hope, I'm just using a term here from the scrap industry, which is called twitch. I'm not sure if that's a common nomenclature in your industry. Martin, I'm looking at you, you are nodding, so I guess I can utilize the, okay, if not, I will introduce it. So twitch is a scrap grade defined by ISRI standards, so by North American standards, but it actually starts to, I think it is being used globally. So we have automotive shredded material, we have an eddy current. The eddy current makes non-ferrous metals. The non-ferrous metals is aluminum, copper, brass, zinc, heavy, in general heavy metals. When you do a separation on this non-ferrous metals, which is called Zorba, so the aluminum and the heavy metals, into aluminum and heavy metals, the aluminum fraction becomes the name twitch. And that's the twitch fraction that you see here. We actually have a process here of material that was sorted in 2 steps, one by X-ray transmission for density, and the second one by LIBS into grain sizes, 10 to 40 millimeters, 40 to 100. And with the autosort pulse, we extracted all alloys with low magnesium and low silicon content. And the flow diagram actually looks this way, and I think I talked about it already. First step is X-ray transmission sorting, where we do rod and cast separation. We say rod and cast, but it is high alloy versus low alloy. So it's not a perfect rod and cast fraction, but the rod actually becomes a good pre-concentrate for the autosort pulse. And then on the autosort pulse, we ejected what is here called primary grade aluminum with a low magnesium content. Actually, the goal was below 2%, when you look at the melt analysis to the right, we actually went well below 1% magnesium content. So that actually this material can be used as a substitute for primary material in the production of 6,000. And then we have a second grade aluminum alloy. So this is a result, a melt result, and this actually yields very good results if you want to make a 6,000 fraction. I will skip the second example. You will actually find the same process in the slides being handed to you, because I also want to hit on post-production scrap applications. So we have on one side the post-consumer applications. The second one is post-production scrap applications. And here you see a quick generic process diagram, post-production scrap from the automotive industry, where 5,000 and 6,000 aluminum alloys in the production process get mixed. 5,000, the one with high magnesium content, 6,000, the one with low magnesium content. The material, the production stamping scrap is shredded. You have an overbelt magnet, fines are removed, and then you have a sorting machine, our auto sort pulse. And this we will do at high tons per hour, and we are aiming between 3 and 7 tons of this stamping scrap, depending on the bulk density. And we will do this with high purities. The goal is here to achieve 95% or better. And these are the results of a first field validation that we did last year with a customer in Germany, where we actually hit on 5.2 metric tons per hour throughput, with a purity of the 6,000 fraction, manually purity of 94.3%, so we're nearly at our goal, and a recovery of the material of the 6,000 of above 90%, which was very good. We did melt tests on the input material on the 5 and on the gained 6,000 fraction. So we produced the 6,000 fraction, and because our input material was a mix of 5 and 6, the leftover, of course, becomes a 5,000 fraction. And you see that from an input composition of 1.6% magnesium, we managed to make a 6,000 product of 0.6% magnesium content and a 5,000 drop material fraction of 3.4%. So for us, that was a very good success, because both of those materials found interested consumers in the aluminum industry in Europe. Looking at this, we have some more challenges, which we think we will be able to prove in our next phase of testing. One of the challenges will be that in the automotive industry, you have rising magnesium content. In the 5,000s, you have everything from 2 to 3%, and then from 3 to 4%, and then you have the high magnesium content, 4 to 5%, the 5182. So here the question will be, can we actually do a subsampling or a subsegregation of depending on magnesium content? And we think we will be able to do this. And then a similar problem appears on the 6,000 alloys, where you have a rising copper content, and also there's a sampling, sub-sorting needed, which we are very hopeful that can be achieved as well, at least to some extent. Now I'm nearly at the end. This development is actually currently, I'm sorry, I didn't translate the full slide, which is currently actually going into a research project funded by the German Ministry for Economy and Climate, and in Germany, where we have a medium-sized recycler, Gerhard Lang GmbH, Tomra Sorting GmbH, providing the sorting technology, an engineering firm, the University of Pforzheim, Novelis as the consumer of the material, and an automobile manufacturer, an OEM that prefers not to be named in public. And these partners form a consortium, which in which we will actually try to prove the development of an end-to-end process chain for new aluminum scrap. So from the automotive production, identification, sorting, smelting, producing a semi-finished product, and then a reuse in automotive components. And that is what is going to happen in this research project, which I can report on perhaps next year because it's just started. We're just supplying technology. This is what I had prepared. I hope this was still interesting, although this is a lot of aluminum topics. I hope that that you find this interesting, because there is a transfer possible from aluminum and the technology to other materials, to magnesium materials or other non-ferrous metals, not to say perhaps even ferrous metals. So this technology actually will help enabling a higher quality recycling. Thank you.
Thank you very much. I think the last 2-3 sentences were very important for us. I mean, for us, it's also important that the aluminium industry is having more innovation in that, because still the aluminium industry for alloying is the biggest single outlet market for magnesium. In terms of time, Frank, I would ask you to answer the questions in the chat yourself, if that is possible. We have a question from India about the efforts in decarbonizing also the Indian market or other markets, and from Ilian 2 technical questions. But everybody is able to look up those questions in the chat as well.
Very good. Martin, I'm happy to do this. I mean, you can always contact me also directly if there are.
Of course, yeah, true. And I mean, you heard from Alma that we are starting up our 3rd working group, and I think you would be a good candidate to at least to listen in sometimes to our sessions.
I'm not opposing. I actually thought that would be interesting, because also, Tomra, we need to learn other material streams other than aluminum. I mean, we're very focused on aluminum, but that problems are in many other material streams. So we need to learn about it. So I would be very much interested.
Very good. Good to hear. Thank you very much.
Thanks.
Coming to our next speaker, who is Armin Buschhausen from Magontech, an IMA member. Armin is Director of Sales, responsible for the European and the North American foundry market. He has more than 25 years experience in non-ferrous metals, but especially in magnesium. He was with very well-known companies, with Rio Tinto, Alcan, and Constellium. Armin has an MBA, International Business, and a master degree in metallurgy. Armin, please, you will talk about sustainable magnesium recycling.
Exactly.
If you can, yeah, if you can share your screen.
Thank you very much,
Yes.
Martin, for the introduction. Can you see my screen?
Yes, very good.
Perfect. So thank you all the participants, ladies and gentlemen, for dialing in to this IMA webinar. I'm pleased to introduce Magontech to you and explain a little bit where we are on sustainable recycling. Our company has headquarters in Australia, so our annual accounts are counted in Australian dollars. For last year, we had 157 million Australian dollar revenues, which is approximately 106 million US dollar. Altogether, we have 4 factories, 330 employees, and we produce basically 2 products. First of all, primary and secondary magnesium alloys, and the other business line is anodes for corrosion protection. Here you see a summary of our locations. I'm located in Bottrop in Germany, where we produce magnesium alloys and do recycling. We have a second plant in Europe in Santana in Romania, where we do recycling alloys and anodes. We have an activity in China with our plant in Xi'an that does mainly anodes, and a new project, Goldmund, in the province of Qinghai. That is a ramp-up phase. Our magnesium alloy cast house is up and running, and I'll speak a little bit later about that as well. Headquarters in Sydney, and we have a tech center in Melbourne. If you see our locations, we are covering pretty much all of Europe and also close by areas like Turkey or North Africa. Bottrop is in the western part of Europe, covering like a theoretical area west and southwest of Europe. Romania is also a good location since there's a lot of like die casting plants in Southeast Europe, and both of our plants have 2 casting lines to provide also backup in case of some technical issues or good interaction to also work with like flexible volume allocations. As we've heard earlier also from Elmar, there's a growing requirement for sustainability all over the world. In Europe, for example, we have a Critical Raw Materials Act established by the Parliament. And this is like legislation at the end of the day. First, you start with a vision, with a concept, with a strategy, but very soon it's going to be translated into legislation. So what Martin mentioned earlier is like the latest review and the latest edition of the Critical Raw Materials Act, according to which like the EU should have 25% of the annual consumption coming from the recycling. And in magnesium recycling, we are well set. There's a big capacity, even underused currently. So that is a clear green from like the magnesium industry's point of view. We can easily match this 25% request. When you talk about magnesium, then of course another point comes into view. The EU would like to have not more than 65% of the EU consumption coming from a single third country, and with all the magnesium, or most of the magnesium coming from China, 90% of the worldwide consumption approximately. That is of course a point that needs to be addressed and seen how this can be and if this can be implemented in the future. But for the moment, maybe a bigger concern in terms of critical raw materials. There are additional legislation like the EU Circular Economy Plan, which is also like law at the end of the day. So this is requesting the use of less raw materials for any products that you would build, less waste and fewer emission. And on the EU websites, you would find like how the concept looks like. So very clear indications how this should be achieved and what are the milestones. Recently, there was also like a new legislation coming on board, like the carbon border adjustment mechanism. For the moment, it's mainly steel and aluminum, and some other products, not yet magnesium, but maybe this kind of additional like tax, CO2 tax basically, for importing material to Europe will be extended to magnesium in the future. So another like point that needs to be considered. And then, as Martin mentioned already, we have like national legislation that comes on top or is even stricter than like the EU rules. For example, the German government committed to a 65% greenhouse CO2 emission reduction in 2030 compared to the 1990 level, an 88% reduction until 2040, and they want to be carbon neutral by 2045. In the US, we see similar similar activities. The current administration has created a national climate task force that wants to reduce by 50 to 52% greenhouse gas emissions in 2030 compared to 2005. And wants to be net zero by 2050. Of course, it always depends on like who is like the ruling government. Are they forcing more this direction, or are they reviewing the targets? So that will be a very interesting topic for the coming months and years. When we look now at like what Magantech is doing in the recycling plants, we have made a study with DLR in the IMA in 2020 to evaluate the carbon footprint of our recycling processes, and using the local electricity mix at that point of time, we established like 0.59 kilogram CO2 per kilogram magnesium for our plant in Germany, and 0.56 for Romania, which are very low values in our opinion, and most probably the lowest and the best of all comparable magnesium recycling plants. It is related to our furnace technology and a lot of measures to reduce consumption. And what we introduced this year is that we have 100% green electricity in Romania. So the CO2 value is further down. We are currently working with like a consultant to get the number for that, but from like a very low level, we're going further down. This can be also seen in like the IMA reports that are available on the IMA website. To give you a summary of how we work, so we typically collect die casting scrap from our customers, might add a little bit of pure mag to fine-tune the composition. We have a two-step melting process. First step, we might add some alloying elements, and some might be low, so we want to be at the right level of composition. We have a second casting furnace where we do like composition test, and then ingot casting belt and packaging station. And this here shows the example of Romania. That's a 2020 level according to ISO 14040 and ISO 14044 standard, certified also by a third party. The type of scrap we are using is typically class 1. So whatever comes out of a die cast process, castings that are rejectors, runners, gates, risers. We could also work with type 2 scrap, which is clean scrap, typically parts that are rejected that have already some kind of steel inserts. The other scrap types are classified in a certain way that we say, is it oily, is it painted, does it have copper rivets or nickel? Could eventually also be treated. So we are expanding our capabilities to work with those scrap categories. Chips is another category where we are looking at a future solution, and then you have dross, oily chips, and post-consumer straps, and all of that is like a very interesting and promising topic for the future, that we want to do more recycling of further categories of scrap. If you now look at the global picture, what are primary magnesium alloy streams, secondary alloy streams, and scrap streams? It's kind of complicated picture. A lot of primary comes obviously from China, going to Japan, to Southeast Asia, using, of course, a lot of that in China directly. There's a flow from China to Mexico, to Canada, to Europe, of course, some of India. So India clearly is growing. and maybe not all single destinations are mentioned here, but you see that it's quite complicated on the global scale. And then there's, of course, from like the Middle East, to producers who could ship primary to the US. And according to our knowledge, that is also the case, like at least for Dead Sea, that they ship quite a volume of primary magnesium alloys to the US. In Europe, you have a secondary flow, so like we do in Magontech and some of our competitors do. So scrap produced in Europe would stay in Europe, but also could be exported to the US, for example. Similarly, like scrap from China could go to Europe, could go to North America, and other scrap from Asia could go to Europe or to North America. And Canada also has a decent flow of scrap to the US. And in the US, of course, there's like an return of remelt ingots from like local die casters through like the remelt producers back to customers in the US. When you think about sustainability, of course, you would say, why is all the scrap exported from one region to the next? I mean, price is the main driver, but what will be the picture in the future? Would there be like a tendency or even legislation to have a near-shoring trend that like governments would impose certain rules that scrap rather has to stay within the region, or will it still be flowing around? Will there be quotas in the future, export quota, import quota, a lot of possibilities, and that needs to be considered when customers make choices about where they buy, what they do with their scrap, if they use remelt or if they just sell the scrap, some of the elements to be considered. What I want to share with you as well is like some comments about Qinghai. I mean, sustainability is also linked to a low carbon footprint on the primary side. So we work in cooperation with Qinghai Salt Lake Magnesium, a producer in the Qinghai province. That producer will bring magnesium based on the chloride salt in the big salt lake to the market. The plant was up and running for quite some time, produced something like 20,000 tons. It's undergoing technical and organizational restructuring currently, but we are very confident that it will be back on the market in the near future. Plant was Qinghai Salt Lake Magnesium was inaugurated by President Xi in China. So it's a very clear, very high level political commitment to develop this province, this option, and this low carbon footprint source in the future. And if we know something about Chinese economy and Chinese leadership, they have a vision, they want to do it, they do it. It's like building an airport. In Germany, we are not so successful with like building airports very fast. So in China, definitely it will work. And Qinghai has one big advantage. In this province, there's a lot of natural water from the Himalaya mountains that are not so far away. So the plant will benefit from 63% hydro power energy. A lot of solar panels have been built there as well. So there are 18% solar energy and 9% wind energy. So altogether, Qinghai province has already in 2020, 90% renewable energy, which then creates a very low carbon footprint, again, measured and analyzed by the DLR. So Qinghai Salt Lake Magnesium together with Magontech will have a carbon footprint of 5.3 kilograms CO2 per kilogram magnesium. We think that is the best in the world, and compared to currently 22 to 24 kilograms CO2 in competitors' pigeon process. Of course, they are also like developments in China to optimize the pigeon technology, come down to 17, maybe 17 kilogram, maybe use a higher share of recycling in the primary, but then you still have a mixed product. So we think with the 5.3, we are really leading the way, and it should be on the market in the foreseeable future. Just to summarize what we can do, we have really a closed loop recycling with the lowest carbon footprint in Europe, with real circular economy, not scrap being replaced by Chinese primary and being sold as remelt. So we do real recycling. We have a very large capacity in Europe with 24,000 metric tons. We have room to grow. So whoever of the audience is interested to work with us, please contact us, and we are happy to speak further. We have the capability to process class 1 and non-class 1 scrap, have an unmatched recycling rate, growing capability for like the less favorable scrap rates, and we'll have like from Qinghai from 2025 onwards, like really low CO2 primary. It was a short introduction to Magontech. My contact details are here, and I'll be happy to address any questions that might come up.
Thank you, Armin. I don't see any immediate questions in the chat. So thank you very much for the presentation. Thank you for giving us the green outlook here as well. And you're right that I think the Chinese industry will also make significant effort into reducing the CO2 on the primary level, and also will establish a more sophisticated recycling industry as it is today. Thanks again. I will come to the next speaker, who is Ossi Ostrov from company AMACOR. AMACOR is the world's largest recycling company based in the US. Yossi has a 20 years business experience in the field of magnesium, both in primary and recycling. He has a degree in mechanical engineering and an MBA degree in business management from the Ben Gurion University in Israel. And I'm very happy that he is giving us the perspective of the North American market. So over to you, Yossi. Thank you.
Thank you, Martin. And for some reason, I can't share my, let me try if I can see, if I can share my screen with you.
Like this green bottom at the...
Yeah, I can see it. Oh, all right.
Yeah, it's coming. Yes.
All right. Okay. Good day, everyone.
Modus.
Yeah, can you see it now?
Yeah, if you go to full screen modus, then it would be even better.
I guess I'm in full screen mode.
No, we see the slideshow on the left bottom. So if you go down to the right, there is a. If not, then go ahead. No problem.
Yeah, I can see what you have. All right, let's walk it this way. So first, good day, everyone. In my presentation today, I will describe AMACOR magnesium recycling activity, our process and quality control. I'll describe our raw material characteristic, scrap types, finished products. I will describe our sustainability approach. And finally, I will cover a few aspects of the US secondary magnesium market. Few facts about AMACOR. AMACOR is probably one of the largest magnesium recycling facilities in the world. We have a nominal capacity of approximately 50,000 metric tons a year. We are located in Anderson, Indiana, in a former GM assembly plant. It's a pretty large facility, over 250 metric tons, square feet. We actually implement a continuous process. We use high degree of automation, using low manpower. We use state-of-the-art equipment, and we guarantee yield of 95% from scrap to ingots. The company has, of course, ISO 9001. Key aspects of our quality control. The most important point is the entry point, just reviewing and make sure that your incoming material is in good quality. We ensure that our finished product meets the ASTM specification or other customer requirements. We are able to verify and monitor the chemistry throughout the process from scrap to finished products. Our process is based on the flow line, which actually ensures that it's efficient, and we keep a high production rate. We have 2 individual production lines that ensure both segregation and also backup capability. And we are able to, we have flexibility to adjust alloying additions and ensure optimal traceability and control of chemistry. This flow chart actually shows our process steps. Each red hexagon represents the testing or inspection point. After receiving the material, we store it in interim storage, and then it is called to process, shredding operation, preheating, melting, where we add alloying element, additional alloying element, and then refining process, casting, and stacking into various configuration. And then it is put in a large warehouse ready for dispatch. We use a few analytical tools in our process. We have a robotic lab, and we also have a spectrometer on our production floor. We use as a backup wet chemistry lab with ICP. We inspect all incoming materials, scrap, and other production materials. Our finished products are cast based according to the ASTM B93M standards, and also meet any additional internal physical and cleanliness standards. Our material, AMACOR, is formally approved for use in the automotive industry and also by tier 1 suppliers that supply parts to the aluminum automotive industry, sorry. We have also the capability to test rare earth elements if required. A critical part of our process is our proprietary refining technology. It allows us to achieve the highest quality material. And we supply material to both automotive industry and to the major aluminum industry that in various fields, transportation, packaging, and aerospace. Our operation is continuous one. We use a high degree of automation and low manpower. We have experienced management and working teams. We're able to achieve high production rate, and we use state-of-the-art equipment. In the left-hand side, you can see our bobcat is unloading scrap from a container. In this case, it comes in a loose state, but most of the time we get it in big bags, which protects much better on the container. Just to summarize our quality system, our process and our plant layout were designed to ensure maximum efficiency and control of all the raw material from scrap to the finished product. we are able to get highest quality ingots, and we also have we make sure that we can keep and ensure traceability and control of material. We have ISO 9001, and the company was certified to use by the automotive industry since 2001, actually right from the beginning of the plant, and used by the aluminum industry since 2002. Important to note that the quality management system was implemented right from the beginning of our production. AMACOR use only what we call the type 1 scrap, and it is the most common die casting alloys, AM60B, AM50A, and AZ91D. And we supply our products to the die casting industry in the US and to the major aluminum companies. Here you can see how we control our incoming scrap. The first important point is the starting one. Just make sure that you get good quality scrap. Once we get the scrap, we check documentation just to make sure that it's in according to what been agreed. We do visual inspection, put it in our ERP system, and then it is stored in individual load and control area. Then we take sample of each truckload, and once it's get to production, we check chemistry to make sure that it meets our standards. We make sure that the yield is high enough and the production rate is kept. In any stage, any deviation of the above can result in a formal complaint, and in certain cases, we just reject that material. Now I will just go for general classification of magnesium scrap, and I'm now referring only to production scrap. In general, you can say that there are basically only two types of, I would say, classification: high-grade scrap and the low-grade scrap. Type 1 material is the only ones that consider to be a high-grade scrap. It is basically gates and runners from die casting operation. Type 2, it's oil-contaminated scrap. Type 3, dross and sludge for magnesium processing. And type 4 is fines and chips from die casting machining operation. As you can imagine, the most desirable scrap is the type 1. It is either recycled internally by the die casting facility, or it is sent to a dedicated recycler under a tolling agreement or any other commercial agreement. Type 2, the oily and patent scrap, it is recycled by dedicated recycler. Type 3, dross and sludge, contains approximately 50% magnesium, and it is either processed by dedicated recycler or simply put in landfill. The type 4 is the fines and chips. It could be recycled by dedicated recycler or simply utilized in the steel industry for desulfurization purpose. Post-consumer scrap, and it's basically old parts. It mainly comes from the automotive industry or used end tools, helicopter parts, gear, etc. This type of scrap is collected by scrap yards that do additional activities such as sorting, removing certain inserts, cleaning, and then it is sent to additional treatment in a dedicated recycler. Important point to note that aluminum scrap that contains high magnesium content, and for example, used beverage cans, It is this type of scrap is processed directly by aluminum recycler and shipped back to the aluminum industry. The reason I am pointing it out is due to the fact that this volume is basically taken off of the internal recycling or primary business. Few pictures of various type of scrap. Type 1, Gates and Runner, chips. The way chips is stored in big bags, it is considered to be hazardous material, magnesium chunks, dross and sludge, and post-consumer scrap, all parts. What we require, what AMACOR is required from our suppliers, and I'm referring to only type 1 scrap. This material needs to be free from paint, inserts, any dirt and oil, should be dry, shouldn't contain any water, shouldn't be oxidized, free from dross, sludge, and flux, and free from any radioactive material, and also other any combustible material, foreign metallic or pressurized vessel are not allowed. It needs also to meet our dimensional specification. Any deviation from the above can result in non-conformance and rejection of that material. And of course, rare earth elements are not allowed. In general, we produce ingots or finished products to two main categories. First is the die casting industry, and we produce the most common die casting alloys, AM60B, AM50A, and AZ91D. And for the aluminum industry, we produce two types of product. We call it MG6, which is based on AM60B and contains minimum of 94 magnesium content, and the balance is mainly aluminum. MG9, which is based on AZ91D, contains minimum of 90% magnesium, the balance is aluminum. We kept the beryllium level pretty low, between 2 to 5 ppm. Our bundles configuration, it's basically, you can see the picture, it is self-palletized ingots. It is based on our 12 kg or 25 pounds ingots. We provide it with plastic straps or steel straps, and we are able to configure various bundles since our stacker is programmable, so we can configure various bundles upon request. Here you can get some idea about our warehouse. It is pretty large, as you can see. It allows us to stage the material prior to shipment and do additional visual inspection, and we implement FIFO system. Few words about our sustainability approach. We believe that responsible recycling or secondary industry, it's an important part of the global effort to reduce greenhouse gases emissions. And recycling or secondary basically reduce the volume of primary production, and it's inseparable from the global production supply chain. We are currently going through a very comprehensive process to reduce our carbon footprint in a significant way. We are focusing on the two major scopes. Scope 1 to reduce our own emission, and Scope 2 is make sure that we purchase our electricity from a reliable source that use alternative sources. In our case, is the Indiana Electrical Company that use solar and windmills. The figures that we are getting regarding the carbon dioxide equivalent are very encouraging, and we believe that we will be less than 1 kilogram CO2 per 1 kilogram of magnesium produced. We have hired a third-party company just to verify and confirm our numbers. so we will be able to share it with you and the public. Another important point that I would like to bring in is that AMACOR is currently evaluating the option to process low-grade scrap and post-consumer scrap. And this is in very advanced engineering stage, and we want to make sure that the market will support it. Few words about the US secondary market. Basically, there are just a few producers such as AMACOR, Magretec, MagPro. And the secondary market is supplied by the above-mentioned producers, but also by European suppliers, either directly from recyclers in Europe or through traders. One important point to mention is that Platts recently changed the classification of this material. It used to be called US die-cast alloys, and they changed it to Platts 93 magnesium, basically to reflect that most of this material is shipped to the aluminum industry and not exactly to the die-casting industry. Just to summarize the current trends and characteristics of the US secondary market, first, it's important to note that during the recent year, we are seeing less and less die-casting activity in the States, and basically it is less scrap available. As mentioned before, aluminum sector is also using aluminum sector. Basically, it takes magnesium units from the magnesium industry. We are seeing large volume that is coming from Europe, and I indicated it before. And finally, the current market situation is, as you probably know, is pretty soft, and we believe that we will see the same. It will remain the same in the first, at least for the first half of next year. So that's about all. Thank you. And if you have questions, I will be happy to either answer now or just send me an email and I can address it later. Thank you.
Thank you very much, Yossi. You can answer, if there are questions, you can answer them in the chat. There are also two questions, or as one question, actually for Armin in the chat. So if you could have a look at that. Thanks again for the presentation, giving us a comprehensive picture of AMACOR, a very long-term, long-standing, valued member of the International Magnesium Association, and also about the view about the North American markets. The Platts information was new, at least to me. So thank you for presenting that. Having spoken that, AMACOR is a very long-term valued member of the International Magnesium Association. We come to our last speaker of today, and it's actually a very valued new member of the International Magnesium Association, a company from Austria called Non Ferrum. And I would like to welcome Peter Scheffler, the managing director of Non Ferrum. Non Ferrum, a company which produces all kind of powders, turnings, granules, and also magnesium alloys. Peter has some experience in the aluminium industry before. He has also gained some international experience as a general manager for BAMCO, the Bahrain aluminium manufacturing company. Please, Peter.
Hello, everybody. I try to share my screen, but it's not free yet. You also have to give it up. Okay. Yeah.
Are you here?
Okay, so I'll try again.
There's no snow in Austria. Come on.
No, this is from autumn. This is my home place, the Tachinger Lake. So I work on the other side. This is Germany, and the other side is Austria. But these are the Austrian mountains. And You see my presentation now?
Yes.
Yes, okay. And this is also the starting point when you see the background where I'm coming from. I think we have a certain responsibility to our nature, and I want to give you maybe some ideas how to improve the recycling or the CO2 footprint. I'm sorry for that. And since I have only 5 minutes left, I will do it quick. As you see, this is our plant on the bottom side. This is our magnesium plant where we do
You
the
can use your
powder.
time, Peter. You can use your time.
I know that. No problem. No problem. This is our plant for magnesium powders and magnesium turnings. So for that, we use pure magnesium ingots from China and from Dead Sea materials. And on the other side, you have the recycling plant. But as you see in the background, you see the same lake, yeah, from the other side now. And all this greenery, I said, we have to do something to keep it like it is. And so I want to show you some options to reduce the footprint or to take our responsibility. Salzburg itself, so it's the region of Salzburg we have for the electricity side, not for the gas side. We have 100% sustainable electricity, and therefore this is for the scope 2 footprint, it's 0. So we have 95% water and the rest is wind, biomass and solar. So I think this problem is solved in the Salzburg region, but it's easy to have all these mountains and all this hydro energy available. This cannot be done everywhere in the world, but we have also seen it from Magontech in China. They also use this power. Sorry. Non Ferrum itself, we have our electricity used is 20%, as you see with this photovoltaic. So this has to be increased, of course. The rest is bought, so it's all renewable, but still I want to increase it. And the company cars we are using are 80% electric. We have one combined electric and combustion engine, which is our sales guy. He needs some range sometimes. So, but this is the last one, and the 4 other cars are electric. So also here we have to reduce the CO2 footprint as much as possible, and we want to keep going. Our production is quite standard. So we have gas furnaces, which is also the main problem for the CO2 footprint. As you can see, this is the melting process. On the other side, this is the casting, which is under atmosphere, but immediately after casting, we go under nitrogen. So the oxidation is stopped after that. And then you see the incoming scrap is also under roof, so it's dry, but still before we remelt it, and it's quite interesting, we put it close to our furnaces. As you see it here, it's a little bit dusty, unfortunately. And with this, let's call it pre-warming, which costs us 0, we have reduced the loss by 1%. So we do 5,000 to 6,000 tons a year. So 1% reduction is 50 tons per year of magnesium we are not losing just to warm it and dry it up within the plant. So this is one option if you have it outside and it is cold, especially now we have -degrees. This helps a little bit to avoid the oxidation. And also, as you see, we have not cut it down to very slow parts. It has a disadvantage that you cannot fill it automatically, so we have to fill it a little bit with handcraft, but also the surface is less, and therefore the burning rate is also less, so the oxidation is also less. Here you can see our finished ingots. I think this is quite standard, and there's one thing which is interesting, and I think this is the main part of my presentation today. I just wanted to show you how we do it. So as you see, this gas, not electric furnaces, but we have found maybe an idea to reduce the gas consumption. And we have therefore a FFG project. It's in the Austrian R&D support. and it is called dust to hydrogen, which means dust is this the dross we produce every year. So as everybody knows here, when you recycle magnesium, you gain dross. So we have roughly 500 tons per year, which has a balance of metal in it of around 20%. So, and it is really hard to use this material. We know that in Czech Republic, the Regal is using it for growing plants. So I don't know the exact name of this product, and they can use it in agriculture. But we did not get the permission on that because of the rest of beryllium in it. So we kicked this away. But the magnesium itself, we can also use in the aluminium industry, but they're also not so happy to have this dross in the aluminium industry for remelting to get this 20% out because of the hydrogen production during the melt. So we wanted to dump it somewhere, but they all said, no, it is too much hydrogen on it. And then in the end, I said 3-4 years before this gas problem came, we should use the hydrogen maybe. And we realized that we generate hydrogen, as you see in the sheet, about 8,000 kilograms per year, which is 80,000 norm cubic meters per year, or relevant to 260,000 kilowatt hours or 260 gigawatt hours of gas. And the question is how you can get this gas out, how you can make it released from the dross. And I talked to several chemical companies because you need acids for that. And within this project, we are looking for the right acid. So it works with standard hydrochloric acid or sulfuric acid, but this has a too high value. So there are roughly 10,000 scrap acids in the market, and we are trying to find the right acid now, which also generates more hydrogen, because in almost any acid you have hydrogen included. So we try to get the acid from the dross, the hydrogen from the acid and the hydrogen from the dross, combine it and use this hydrogen then for our burners. At the moment, you can have around 20% of hydrogen you can just mix with your standard natural gas. The reason is not the burn itself or the danger. The reason is the pipes. So the actual pipes you have can only take 20% of hydrogen, because hydrogen is going through the tubes itself. I only know the German word, sorry, not the English. And so we have to build up a new pipe system which can transport the hydrogen, and then we can also increase, I think, the hydrogen content for the burners. And at the moment, we generate, as you see here, 25% roughly of hydrogen, and we try to blend it and we try to mix it, and then we can reduce our CO2 footprint, as you see in the next sheet. So we are not as good as Magnotech, but I think Magnotech is using electric furnaces, or at least a mixture. We have only gas furnaces, and therefore we have a big input on gas. We also have magnesium. You know, when you use scrap, you also have to add some pure magnesium. We try to use also this ICL DSM material as much as possible. So we use that, and it is also reducing the CO2 footprint in common. And you see at the moment we are at a CO2 footprint of 0.77 kilogram per kilogram magnesium recycled. And with the usage of hydrogen from dross, so this is a project, as I said, and I hope it will be successful, we can go further down to 0.73. So this is quite in between of AMACOR and Magnotech, and I think it's the actual range. But I want also to tell you this could also be done, I think, at Magnotech, AMACOR, and all the other recyclers. So I don't want this technology used only for us. I want to improve the whole magnesium situation, the dross situation. And I have not tried it in the aluminum industry, but I know that there's also scrap, there's also hydrogen in it. And so maybe this is also an option for the aluminum industry, which is a much higher factor. So we have not enough, we call it green hydrogen production. As you might know, in Germany, they want to do the steel production with hydrogen. And if you take one of these furnaces, you would need 10 times the hydrogen which is available at the moment today. So the problem is just the production of hydrogen. And therefore, if you find other options where you could get it with scrap acid and dross and other scraps, it might be an option, maybe also for the, not for the class 1 scraps of magnesium, also for the lower classes, which cannot be used, as you know, because of all these impurities. So this is my idea today. I hope it was interesting and maybe everybody can copy it or improve it even. And I say thank you, and I'm available for questions anytime, as you see here with our email, or I think you have the contact. Thank you very much.
Thank you, Peter. You have not mentioned the patent on that, so no. There's a question in the chat about if there's any waste using the acid during the process.
Again, the waste.
If there's any waste produced when you use the acids in the hydrogen production.
Yeah, of course. This is the part of the project. What you have is dross and acid, and you gain hydrogen, you gain water, and you gain salt. So the question is how you make the chemical process to get a salt which can be used in the end. And this is of course, the most difficult part, because if you produce then a more dangerous waste, then it makes no sense. But of course, there is waste which is a certain salt, which depends on the acid you put in the beginning. Still there, Martin?
Yes.
Yeah.
Okay. We'll just put on the closing chart of today. So thank you very much to all the speakers. Thank you all the participants. This is only the first session. We are offering a second session later today at 8 o'clock in the evening, our time, which will be moderated by my colleague in the US, Rose Eaton. She is the new representative of IMA representative of the North Americas. So thanks again for listening in. You will receive in a few days a link for the presentations, and I think we need a little bit longer to publish the recording, so please share it. You see that the IMA and also all the magnesium recyclers on a global base are prepared to take on the future challenge of recycling for magnesium, also partnering with the aluminum industry, and we look very much forward to a good network and engagement within the next years. Thank you very much for listening.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Bye-bye.
Thank you.